Hello everybody. We have learned about the electric field. Let's do a small repetition. Maybe you live close to a 5G antenna and you are worried about your health. So what you will do is you're going to go and measure the electric field. And where are you going to measure? Well, it's at your house. So you can go to any place in your house close to the antenna and measure the electric field there. So this is the idea. Even though if you do not see the antenna, so if it's just somewhere, you can still go here and here, wherever you want, and measure the electric field. And to measure the electric field, it was just the force on the charge that is inside here divided by the charge giving the electric field. However, there is now a different approach. Instead of just measuring the electric field, we can say, well, if the source is known, we can calculate the electric field at any position around or in the environment of this antenna. And that's what we want to do today with the most simple way, which is just one single charge in the center. So this is chapter 18.6.1, the point symmetrical field. So we have a charge somewhere. So let's take it a positive one, which is here the source. And we want to check what is the electric field at any point around this charge. For example, over here. And what is the electric field? The electric field is the force experienced by this test charge Q0 that we have put here. Q0 is defined to be a positive one, so we have here a positive, so it is repelling, so the force will be opposed, and therefore the electric field will be opposed. So we can draw a small arrow at this position. Of course, we could do that at any position in the space. We could do it here and here and here. And if the spacing from the source to this test charge is equal all over, then the electric field has the equal strength. On the other hand, if I go closer to the charge, the electric field will be stronger since I'm closer. So for example, here and here, the field will be stronger. The direction of all these electric fields is always pointing outward, starting at the source, and it's getting weaker and weaker the further away we go. So we can just draw some helping lines to visualize that. So I just draw here lines like that. And these lines some sort of visualize the electric field. How can we now calculate it? For the calculation, we follow up here and we know what the force is. So if we have here a test charge and the source charge, we know that Coulomb's law is given as K times Q of the source times Q0 over R squared. And this we have to divide by Q0. We can simplify. The Q0 drops. That makes sense, since the larger the Q0 is that I put here, the larger the force. So if I have double Q0, I have double the force. So I divide it, I get rid of it, and I just see the effect of this source charge. And therefore, the electric field for this point charge reads K times Q of the source divided by R squared. Let's do an example. What is the electric field at a distance of 15 centimeters from a point charge of negative 0.05 microcoulomb? We could draw the situation. We have this source charge. So I draw it here, minus 0.05 microcoulomb. And we put the test charge, which is over here, and we can calculate. The electric field will be K times the source charge, and I just take the magnitude over R squared. This amounts to 19,978 Newton per Coulomb, or we can also say it is 20 kilo Newton over Coulomb, which is the same. I have just now not written the negative sign, but we can see here negative positive is attracting, so the negative sign basically is just telling us that it is attracting, so the electric field will point to the left. If we had this test charge at the same distance from the source, but maybe further down here, then the electric field is still pointing towards the negative source, so we just had it here. Therefore, for the electric field, usually we just give the magnitude, here the positive value, and in the drawing we then can also show the direction of the actual electric field.